Thank you all for joining us today. My name is Gary Schindel. I'm the Administrative Vice President for the National Geological Society, not the U.S. government. Thank you all for joining us. Last year at the NSS convention, myself, Dave Hughes, Ernst Castine, Alex Sproul, and some others got together and talked about the interest in trying to have some of the NSS luminaries, the folks who really have been involved in the society for many, many years, take the opportunity to make presentations on their caving career, their professional career, etc. And we've been very fortunate. We've had 3 of these lined up this year. Jeannie Gurney, some of you all hopefully were able to see her speak yesterday. We have Will White today, and we have Dwight Deal tomorrow. And so what I'd like to do is turn this over to Dave Hughes, who's going to introduce Will. Thank you all for coming.
Good afternoon, ladies and gentlemen, and welcome to the second in the Luminary series. A few housekeeping reminders before we begin. The entire proceedings today will be both audio and video recorded, so please extend the usual courtesies that you would when recordings are in progress, including turning off your cell phones and other noise-making devices. Will has kindly agreed to hang around in the hallway for a little bit after his talk. If you have not had an opportunity to meet him in person, that would be an excellent chance to do so. So thank you for that kindness, Dr. White. It's a privilege indeed to introduce Dr. Will White, a man who is one of the true pioneers in the field of cave science. Will has enjoyed a very distinguished career at Penn State University, where Will, his students, and his former students have in the past and continue to make groundbreaking advancements in the fields of cave science. Will began attending NSS conventions in 1954, and believe it or not, has been at every single NSS convention since then, never breaking that continuous streak. A record that perhaps will not be broken by anyone except his wife. It's my pleasure indeed to introduce to you Dr. Will White, in my opinion, one of the most respected, most quoted, most recognized, most honored, and in my opinion, one of the most loved cave science people in the history of the field. Please enjoy your afternoon with NSS Luminary, Dr. Will White.
You know, I can't believe Dave said all that stuff with a straight face. But, the point of the discussion this afternoon is how cave science evolved and how I guess I evolved with it. To begin, John Milroy, who apparently hasn't shown up, or at least didn't have the nerve to show up here, has a thing he bounces off his students. He says, you know, a light bulb is not really a source of light. It's a dark sucker. The light is there all the time, but when you turn the bulb on, it sucks up the darkness and you can see the light. And then he asked the students to prove him wrong, of course. But it occurred to me that's actually a pretty good metaphor for science. The facts, the laws, the information is already there. It's just we can't figure out what it is. And so it's a question of pulling away the darkness and trying to find the light that's underneath, which for cavers is also a pretty good metaphor. So this is supposed to be partly autobiographical. So we begin at the beginning. People have asked me a lot of times, when did you become interested in caves? And my honest answer is, I don't know. This is the little one-room school where I went to grade school. That's been closed for a long time. It's actually under a lake at the present moment. But they didn't have school buses when I went to school there. But I would sneak off from school and go off into the woods hunting for caves. Well, it turns out that the countryside out there is all shale, which is not a great place to start. But in fact, did find that thing on the right is a thing called the Panther Caves out there in southern Pennsylvania. It's a tectonic cave. It's a place where a big block of rock has broken loose and slid down the hill a little bit, and there's little tectonic caves in there, 6 of them or so in that little canyon. Not bad. Okay, there we go. I went to college, a little school called Juniata College in Huntington, Pennsylvania, actually in my hometown. And in college, needed a summer job. And the managers of this little show cave called Lincoln Caverns, which is out the road, were also Juniata graduates. And they gave me a job being a cave guide. Now that is a job that I highly recommend for budding academics or teachers of any kind, because, you know, there you are, you're handed this group of people, and you're supposed to show them the cave. There's Pa. He didn't want to stop in the first place, and he's grumbling about how much the tickets cost. There's Ma. She's absolutely certain that the whole place is crawling with snakes. There's the little one who's afraid of the dark and doesn't going to win that place. And there's the teenager who thinks it's great. So somehow you got to bring all four of them through the cave and back out again, thinking they've had a great experience. And if you can pull that off, there is no classroom in the country that's scary. But I did get started into real caving, and there is this, one of the first ones is one called Kukan Cave. It's in Huntington County, central Pennsylvania. It's got an entrance shaft, about 160 feet, 180 feet deep or so. And we went scrambling down that thing, dropped some good old hemp rope down and clambered down, and there I am. You notice the caving gear, right? And explored a good bit of Kukan Cave. Got in there one time, and this is an object lesson in why it is very important for folks in the NSS to take care with these idiot spelunkers that they run into every once in a while, because we're some other real cavers, I guess they were real cavers, who met up with us in there one time and just gave us hell for going in the cave and essentially, untrained, unequipped, anything, and essentially ordered us to stay out of the cave. And I'm thinking, now come on, put it where the sun doesn't shine. And obviously didn't stop caving. But my NSS number is considerably higher than it would have been if those folks had been a little kindler and gentler. But it wasn't all those kind of people. Coming to Lincoln Caverns back in around 1951 or 52 was a former NSS president, Dr. Ralph Stone. And Dr. Stone, along with Bill Devitt and Bernard Smeltzer, were collecting information for NSS Bulletin 15, the 15, the caves of Pennsylvania. And he said, we need to know where all the caves are in the state, and if you can find caves, let me know. So I hunted around, and there was a short list of caves in the general area I stumbled onto. And if you look at NSS Bulletin 15, you could call those four little short cave descriptions my first publications. Because if we're trying to develop science, you look at the traditional scientific method, step one is observation. And in this case, observation means find the caves, and it also means map the caves. Well, I did actually manage to make it through college in spite of all the caving, and went to Pittsburgh to work for Mellon Institute, a research organization that was built on the style of the Parthenon. And a number of things. I came in contact with the Pittsburgh Grotto, became very active with them, and was doing a lot more caving than I was graduate study, which was getting me into some trouble. But it got me access to things like emission spectroscopy for chemical analysis, X-ray diffraction for mineral identification, and lots of other things. And I started to figure out what exactly is cave science all about. And one of the revelations that happened, I think it was at about 4 o'clock in the morning when I was doped up on much too much coffee and expecting to leave at about 7 o'clock in the morning for an NSS convention to give a talk that I hadn't finished yet. And it occurred to me that all this analytical data didn't do me any good at all. The important thing in the earth sciences is the interpretation. It's a deductive science, not primarily an analytical one. But we got some things started. The first talk on cave science-related stuff dealt with cave coral and consisted of taking some bits and slicing them up and looking at the way the stuff grows and come up with some ideas on how this stuff might have formed. We're looking at weird minerals in the Vanport caves, which those of you who come to next year's NSS convention may have an opportunity to see if you take advantage of the opportunity for some cave camps in western Pennsylvania. Looking at calcite versus aragonite and why is there one rather than the other, and that kind of thing. Maybe that is speleology. We talked about speleology in the U.S. in those days, but I don't think we had much of an idea what it was all about. And we're competing, and Jeannie was mentioning this in her talk yesterday, that, you know, when she and Russ showed up at that international congress, and the local folks said, what the heck is these Americans? You know, they ride in on horseback. In Europe, by the 1950s, there's a well-developed science of caves. And I want to make a plug here for, I think, the person generally should be considered the father of European speleology. Not Martel, who came along later, but Adolf Schmidl in Austria, who was writing magnificent descriptions, geological descriptions of caves, mostly in Eastern Europe, in the Austro-Hungarian Empire, so that by 1933, it was possible for Professor Dr. Georg Kirli to actually publish a monograph on theoretical speleology. And the French had their volume, and in the United States, there we are, the professionals, right? These guys, like Davis, who is over here, and Brett, who is here, are having their big idea that somehow caves are formed by slow-moving water deep below the water table. A.C. Swinnerton, who actually had some NSS connections, was saying, no, caves are formed by fast-moving water very close to the water table. The problem for any sort of cave science in the U.S. was that in the geological community at large, the response was, who the hell cares? But meantime, the observation, the step one of constructing a science is going full bore. Exploration. Where does the cave go? Well, it occurs to you, if you think about it, you can't see a cave. If you're interested in the landscape, you can always climb up on the mountain and look out over the countryside, and you can see the hills and the mountains, or you can fly over in an airplane, or satellite images, all kinds of wonderful things. You can't do that in a cave. All you can see is a little piece of the passage that you happen to be standing in at the moment. So you need detailed mapping, photography too, to show what the cave actually looks like. The danger of not knowing got Davis in a lot of trouble back when he wrote his paper, because he really didn't know what caves looked like. He was hypothesizing. And then you figure out that caves are pieces of something that don't really end. Roger Brucker pointed this out clear back 1966. Look, you got a passage ends and breakdown here. You got another passage that ends and breakdown on the other side. Maybe they're the same passage. And you can figure out, that's why people are busy digging breakdown piles these days. And eventually you figure out this is all part of something much bigger. So while I was in Pittsburgh, we put a lot of emphasis on a little drainage basin. It's about 40 miles north of here. The drainage basin of Oswego Creek. That's what the place looks like. That's the Tub Cave sinkhole for those of you who know the area, the Dry Creek Valley. There's a cave entrance over there. It's a very nice little closed basin. There's places where the water runs in. There's places where the water runs out. There's wet stream passages, there are upper level dry passages, and the question was not just exploring the caves, but how does all this stuff fit together? And so in order to do that, this is a map that was drawn clear back sometime in the 50s, but we've got a number of caves shown by these red lines. That's Overholt Blowing Cave for people who know what the thing is. And the question is, how are all these things connected? Which means that you need not only cave surveys, you need precise overland surveys to link up the entrance. And to go back to a personal note, at the moment, I was trying to figure out how to get all these things surveyed. I needed somebody who had access to and knew how to run a transit. And I found out that there was this person at the University of Pittsburgh Civil Engineering Department, known as Liz Loxley, the lady engineer, who would do that. And so she came down to Oswego Creek, and one thing led to another. And she's still sitting here with me 50 years later, so. Other things happened during those Pittsburgh years. Among other things, they kind of expanded our horizons a bit. There was an expedition to the Yucatan, which didn't produce a whole lot scientifically, although it's a pretty neat place. An expedition to Jamaica that produced an article by Bob Dunn and I in the NSS Bulletin. And then an expedition to Venezuela, where we had the bright idea of trying to get back to Angel Falls, which we didn't entirely succeed in, but we were around. That's Angel Falls, and seen from the air, and looking at this stuff on top of the mountain, on top of Ollantaytambo. This is a very massive rock called the Roraima quartzite. And I went, geez, that stuff looks an awful lot like karst. And getting down on the ground and finding little solution features and stuff like that. So my gosh, you can actually not only have karst and limestone, you can have karst and quartzite. And so that was written up in as far as I know, one of the first papers written about quartzite karst. And now, of course, we know there are giant caves in this same Roraima formation down there in Venezuela. Still don't understand how those things got there. Now, another question that I get asked from time to time is, well, what did you do your thesis on? Because, the job in Pittsburgh turned into a dead end. There was definitely a dead end. And I got to get out of there, and I need to get another degree, so I've got the proper union card for doing other things. And so I went to Penn State in 1958, graduate school. So everybody seems to assume that I must have written a thesis about caves. Now, writing a thesis about caves in this particular time frame, as Dwight may tell you tomorrow, would be something close to suicidal. Well, actually, what I did my thesis on was thermodynamics and phase equilibria in the lead-oxygen system, and the essential part of this, as far as my advisor was concerned, is that he had found somebody who was had a sufficient guts-to-brains ratio to pump oxygen to 60,000 pounds per square inch into a pressure vessel and then heat the pressure vessel red hot. I discovered that these turbine blade steels that we made those pressure vessels from was really pretty good stuff because they didn't blow up very often. And I mapped out a phase diagram for a lot of stuff like that and went on in other directions, got invited to stay on with a laboratory, materials research laboratory, which was being put together at the time. Also got invited to become a faculty member in the Department of Geosciences. So I made the transition from being more or less of a physical chemist to being more or less of a geochemist, a spectroscopist, a materials scientist, a hydrogeologist, or something. I have tried for years to figure out what I am, and I haven't succeeded in doing that. But science is moving along. At the same time, I'm gradually moving along from being a caver, or only a caver, to a cave mapper, to more or less scientific interests. Science at large is moving. And if I had to hand the credit to any single individual, realizing there's a lot of individuals, it would be to a former NSS president, William E. Davies. Now I got to admit, I after all did name a passage in Overholt's "Davies didn't crawl" and things like that, but Bill really did the job because, among other things, he organized a meeting at the American Association for the Advancement of Science, Chicago, in 1959, and he managed to get some of the old-timers, including no less a personage than J. Harlan Bretz, to come to this meeting, and he had a certain number of what I might refer to as the young smartasses also show up and give talks. And these were all published in the NSS Bulletin back there about 1960 or so. And as a different way of looking, we weren't talking vadose-phreatic kind of stuff. We were talking from a somewhat different point of view. And to make, so the paradigm shifts are pretty minor, but we're also borrowing concepts, methods, and stuff like that from other disciplines. So instead of moving inward to a science of speleology, we were moving outward, trying to correlate caves or connect caves with various other parts of the scientific community. In the meantime, at about this same time frame, the Cave Research Foundation was getting itself put together with the task of trying to survey and understand, well, at that time, the Flint Ridge cave system, but also Mammoth Cave and the whole complex down there. And I got invited to come down and start up scientific projects. And again, this same advisor who was perfectly willing to have me pump oxygen to 60,000 pounds per square inch was perfectly willing. He said, okay, go on, go down, for a month, right when I should be writing my thesis. And spent a bunch of time looking at sulfate minerals and sediments and breakdown and all kinds. It was a real great couple of summers. But the way of looking at caves is gradually changing from caves as features that require an explanation, like where did it form with respect to the water table, to caves essentially as pieces of pipe that are carrying water through the aquifer. And if it's pipe carrying water, that's something about which a lot is known, and it's known by the civil engineers who teach courses in things called fluid mechanics, which is something that a geologist typically would not know the first thing about. Well, I had a consultant pretty close to me, very close in some cases, and so put some of that together and raise questions like, well, how come we got caves? How come we got long, continuous conduits? Why not the limestone just dissolving like a piece of cheese? Why doesn't all the acidity simply get neutralized when the rainwater hits the limestone surface? How do you get unsaturated water down through the aquifer anyway? So we cooked up. He was sitting talking about the mathematics of this stuff with Judy Longyear, who was a mathematician or a mathematics grad student there at Penn State. And somehow put together this thing. I love the title. It's one of the best titles I've ever written. I don't know if any others any good. It never got any farther than the Nittany Grotto newsletter. But that paper, I saw it cited in a European journal within the past year. They're still citing the Nittany Grotto newsletter, which I thought was pretty good. Well, the question eventually got answered. The idea was, okay, if the water moving through is like a pipe, it's going to be moving in turbulent flow. If the turbulent, you stir your coffee, the sugar dissolves faster. Maybe that would do the job. I put that together, and Rain Curl shot it down and said, nah, it ain't going to work that way. But it turned out it was on the right track. We didn't answer it for about another 10 years or so at an International Association of Hydrogeologists Congress in Huntsville, Alabama, where we worked some calculations with, that's me and Jack Daniels over there on the side. They showed it really was peculiar things in the kinetics of limestone dissolution. And that particular idea, which went from the Nittany Grotto newsletter to this paper, has gone on, and Wolfgang Dreibrodt at the University of Bremen, Germany, and Franzi Gabrishek at the KARST Institute in Slovenia have generated some beautiful computer models following this up. So this has gone a long way from way back then. So, okay, let me summarize for a moment. You know, I'm trying to parallel career and science at the same time. I couldn't really figure out a very good way of doing it. But from 63 onward, yeah, I was at Penn State. I never left Penn State. I still haven't left Penn State. I will probably leave Penn State in a box. So the career path is pretty boring. But I've done a lot of other stuff because there was, again, something else here. It wasn't the cave and karst science that got me a position at a major research university. In fact, I was pretty darn careful not to tell anybody I was doing this stuff. You know, I think my colleagues, some of them at least, knew about it. It was a kind of a don't ask, don't tell kind of approach. But I was doing, I was listed up there, all kinds of other things. And, you know, so the career path went along reasonably smoothly. But what it gave me was a platform. I had an academic institution, which is not a bad place to be if you're looking to do things like cave science. I had the at least possibility of getting some money, not much, at least initially. And I had access to a lot of nice high-tech equipment I certainly wouldn't have had otherwise. But probably most important is that I had a lot of very good, very hard-working folks who were willing to take their chances writing a thesis about caves and karst. And that's a list. And I want to here publicly say thank you to all 18 of those individuals, several of whom are in the room. You know, it's like having lots more hands, and more importantly, lots more brains to bring to bear on a lot of these problems. So we could do quite a lot of stuff, even with kind of keeping it sort of in the closet for quite a while. So the question then was, how would you manage to link karst science, or caves and karst, to science at large? And the one obvious link was hydrology. And so as we'd already figured out, you know, the cave systems, once you start looking at the full drainage basin, all the infeeders and the springs and the caves streams, try to put it all together, it's pretty clear that you've got a drainage system which is very different than the textbook aquifer. And Vic Schmidt and I wrote a paper way back in 1962 or so, which essentially pointed that out using the Oswego Creek Basin and using Hermine Zotter's extensive dive tracing results in the basin as a basis for us, because cavers get kind of intimate with the hydrology in the process of doing what they do. But it took a while to get this point home to the hydrological community, the professionals. In 1965, I had presented a lot of this stuff at a talk at an American Geophysical Union meeting. We're now moving outside the NSS into the professional community at large. And there in the audience, in the front row, was none other than M. King Hubbert, whom some of you know of in Hubbert's Peak with regards to oil. So a very, very famous guy who wrote back in 1940 the fundamental paper on groundwater flow. That is a great classic paper. It lays the whole thing out as a flow field of potential lines, solution of differential equations. It's fantastic. And I give my talk about cave running through, water running through pipes and stuff like that. And good old M. King Hubbert comes roaring to his feet at the end of the talk, turns and faced the audience and said, "What you just heard is total nonsense." I was never more pleased to have such a person proved wrong. But to show you where it's gone, I mean, this was the attitude. I mean, yeah, there's a lot of people who weren't as prestigious as Hubbard were saying exactly the same thing. But back, I think 1969, the NSS, 68, convention in Missouri, I didn't have a talk. And I thought, oh boy. So how am I going to justify going to the convention? So I sat down and I drew a bunch of what essentially are little cartoons of how groundwater might flow through rocks and put those together, and okay, now I had to talk, and it was fine. Jim Quinlan comes up and says, hey, that was great, are you going to publish it? Me, publish it? No, I wasn't thinking of publishing it. Why, you got to publish it, as only Jim Quinlan could do, for those of you who may remember him. So I wrote this thing called Conceptual Models for Carbonate Aquifers. It was accepted by Groundwater, which is a professional journal. It's not a caving journal. And not only that, I got an email from the editor, I don't know, 6 or 8 months ago, asking my permission, and damned if they didn't reprint the thing as a historically significant paper. And the only reason that was ever written was I didn't want to come to a convention without anything to say. So, out of all of this, how do you create a science of karst hydrogeology? Well, you've got to use the notion of groundwater basins, you can use water balance, you can do storm hydrographs at springs, chemical variability of spring waters, contaminants, contaminant transports, sediment transport, a lot of stuff. And where the subject has gone today, of course, is that people are combining this into very elegant computer models. So they hope. So I'm going to run, I'm going to try to walk through a whole bunch of examples of where this thing is gone. This kind of sets the stage for all of it. Groundwater basins, this is Jim Quinlan's map of the Mammoth Cave area, an absolutely beautiful piece of work with probably 500 or 1,000, I don't know, a large number of dye traces. We learned, of course, that karst springs tend to be very flashy. They respond to storm flows, as any caver who's ever been trapped in the cave by rising water knows very well. And so you can actually measure the discharge, look at the shape of the discharge curve, and from that you can calculate various things. Somewhere along the line, we thought it would be an interesting thing to look at the chemistry of the water rather than just the quantity. And so Evan Schuster, who was a master's student, an early one of mine, had a series of about 20-some springs there in central Pennsylvania, and he would go out once every 2 weeks, get a water sample, make measurements, and calculate. And he found some springs are pretty constant, chemistry-wise, some jump around all over the place, and worked out some things from that. And then Jack Hess, another student, worked in the Mammoth Cave area some years later, monitored us continuously and found all kinds of weird little wiggles and jiggles in the hardness data of the water, which can be interpreted in terms of infeeders coming in and so on. So there's a huge amount of information you can get this way. Also started looking at contaminant transport. It turns out you can, let's see, what all can you do? This, you don't believe there's contaminated karst aquifers. This is the spring discharging the water from the Obi River in Tennessee. Turns nice and blue because of particulates suspended in the water. Or as you go over into the west branch of the Obi, there's water that's polluted with mostly aluminum, not iron primarily, but mostly aluminum, presumably coming from the old coal mines up on the Cumberland Plateau. And we did a whole bunch of stuff with that. Dorothy Vesper, another student, was looking, if you want to look for metal contaminations, an Army base is a good place to look. And this was done out of Fort Campbell on the western Kentucky-Tennessee line out there, and she was able to show the metals like lead, yeah, surprisingly, nickel, chromium, arsenic, iron, all track with the aluminum, which is essentially tracking with the clay minerals, which is essentially the turbidity of the water, which means you get a storm, hydrograph goes up, the calcium type or the carbonate type stuff drops down, but you get a peak because of this stuff riding the clay minerals and coming through as the muddy water. And most recently, we've been looking at sediment transport in caves. We know about sediment piles in caves. We see those, actually measuring the amount of sediment that comes through. This is a picture that Garrett Seymour took during the hurricanes that came through Pennsylvania about 5 years ago. And there's no much question about there being sediment going into the cave. So hydrology goes on, and it's moved on. I am not into writing computer models, and I have a deep-seated suspicion of computer models because of these couple of reasons that are on this slide. There's other things that one can do, and I'm going to try to do these fairly quickly here. KARST morphology, which was probably the oldest branch of the subject. Systematically, KARST morphology has been credited to Hoban Svic, who's over there, stern Serbian countenance looking out at you. And he had a pretty good karst area to work with, being the Dalmatian karst of what is now Croatia, Serbia, Slovenia, so on. But there were two ways of going about that. One was to walk, the old way was to walk up on a high ridge someplace, look at the landscape, and then think real hard. And that was the William Morris Davis approach. Today, what people do is go up on the high ridge, inspect the landscape, and then try to figure out how they can quantize what they're seeing, and then whether they can correlate this to any sort of laboratory procedures. So we've tried our hand at doing that sort of thing. There, in the process of Bet's thesis work, she had occasion to actually measure the depth counting contours on something over 5,000 sinkholes through the Appalachians, and find out that you can fit these to a nice exponential function. And it turns out the exponential function is independent of rock type, which is interesting, but otherwise, you know, okay, that's a nice line through data. What exactly does that mean? Or one can look at cave lengths, which are conveniently available in Bob Golden's long cave database, which is a very, very valuable asset to people other than people trying to figure out where they rank on the list. And Rain wrote a thing on the fractal mathematics of caves a number of years ago. So take his equation, find a very nice straight line. We can calculate a fractal dimension, and then we say, well, what's that mean? And we're into this, you know, analysis is not deduction. You get a result. Now, what the heck does it mean? And we're still trying to figure that out. And we can also tackle the geomorphological part of it chemically. You can figure out limestone is dissolving, the limestone landscape is slowly degrading. You can actually calculate it in a rough sort of way. And then with those kind of numbers, you can work backwards and take something. I've done a number of examples of this stuff, but this, since we're in West Virginia, this is the Smokehole Gorge, which again is only 50 or so miles to the north of us. Here is a big anticline with capped with a resistant quartzite, which has been eroded down so that you have Cave Mountain Cave sits up at the crest of the end. That's a limestone outcrop along the top of the mountain. And it's up there, the cave's at 183 meters, the river's at 408 meters, 275 meters of relief. You use these rates and you back calculate, and you figure out the top of that mountain started eroding about 9-10 million years ago or thereabouts. You make similar calculations in the Cumberland Plateau and elsewhere and get roughly the same answers. So you trace caves, karst, back to maybe the mid-Miocene or thereabouts, but presumably the landscape has been eroding since all through the Tertiary and maybe through most of the Mesozoic, and you figure out what the heck has happened. We've got a big blank space because the numbers we get working backwards don't agree at all with the traditional geologic interpretation. Another small mystery to deal with. And finally, on this sort of very, real fast summary of some things that have been going on, not only by me, but by a lot of other people, probably the most important thing that's happened in the last 20 years has been discovering that speleothems are actually pretty darn useful as paleoclimate archives. And it's not too hard to figure out. I mean, there is Ruddle Cave, which I heard in the Hellhole talks yesterday, might be sitting right on top of part of Hellhole. But at any rate, take a look at that thing. You see, there's a lot of old speleothems, right? Then something happened, and the whole thing got all mudded up and sedimented and covered, and then we got this thing growing on top of it. And that is, 3 feet high or so. That's fairly old stalagmite. It's been growing there for a long time. So there's a lot of events that happen that are visible just in that one frame. And what is unknown, of course, is the time scale. When did all those things happen? Derek Ford, Henry Schwartz, their students and colleagues up at McMaster pioneered the use of uranium thorium dating. So you can, at least back as far as the mid-Pleistocene, you can put numbers. And it was also known that speleothems are luminescent. They glow under ultraviolet light. And back in the 80s sometimes, Yegor Shopov, Bulgarian scientist, found out that if you look at this stuff under a microscope, that luminescence shows a very fine-scale banding, which he interpreted as being an annual, like counting tree rings. And the other thing that happened, more borrowing, shall we say, in this case, heavy ion mass spectroscopy, you can now do uranium thorium dating on very small samples. And so you can actually construct the age of a stalagmite, plot it out, and you can discover that this one, which is one of Stein-Erik Larsen stalagmites, started growing about, 8,200 years ago, and it grew, that's sort of right after the end of the last ice age over there in Norway, and grew to about 6,000 years ago and then stopped. So you can think of these things as being drill cores that you get without the necessity of drilling. And this is a booming business right now. The journals are full of papers. You can measure growth rates, textures, mineralogy, oxygen, carbon, hydrogen isotopes, trace elements, color, luminescence, and so on. Only we've got this problem. And that is we've got a fantastic record, and we're busy trying to figure out how to read it. That was probably one of the classic ones, Jeff Dorrell and his colleagues. These are caves out in Missouri. CC is Crevice Cave. But he's able to distinguish between where the landscape above was forest, savanna, prairie, more forest, through the last major ice age. So anyway, to bring this thing around, and I am at the end of my time, and I'm going to wrap this thing up, cave-related science has come out in several senses of the word. There's no longer any need to hide in the closet. You can submit your papers to any appropriate journal. They'll get the same respectful reading that any other subject would get. There are books. All the current knowledge of speleothem dating and so on, speleothem dating and speleothem paleoclimate is in that book that Ian Fairchild and Andy Baker just published a matter of months ago. A lot of it is summarized in that's the second edition of the caves that Dave Culver and I put together. Covers a good bit of both the biological and the geological side of the subject. So scientific progress has been made. Following the old Thomas Kuhn model of paradigm shift is you had an old dogma. A few people got some new ideas. Everybody else thought they were crazy, but they kept persisting until eventually they were proved right. Then that became the new dogma. Plate tectonics is probably the best sample we have of that right offhand, because there are a lot of people who really didn't like plate tectonics 40 or 50 years ago. But the characteristics is what you might call a first order paradigm shift. Now, a lot of, a real barrier to overcome, a lot of energy to expend doing it. But there's another way of doing it, which just sort of slides sideways and nobody even notices. And that's what happened with cave science. It went from something that the respectable people wouldn't admit in public to something that's filling the journals, and people like Elsevier and John Wiley are publishing books about it. So cave science, after half a century, new day of lots of fabulous exploration. The Vedo-Phreatic thing, okay, it sort of faded away. All kinds of new ideas on other hydrothermal caves, sulfuric acid caves, mixing zone caves, lots of stuff. Speleology, yeah, there's still a lot to learn about caves. Hydrology and paleoclimate are probably the two big deals in the earth sciences. And with that, thank you very much. Okay. Questions? Anybody was asking for them?
Will, is there still a lot to learn? Is there still room for new scientists?
I think it's a big tent.
It's a big cave.
And if you bring in some new experimental skill or new instrumental technique, you're even more welcome. Okay. Okay. I think.
Yes, Roger.
You showed a long list of students, 18 I think you said,
Yeah.
but if you take into consideration their students, how many people would you think would be on that list?
Well, I'm down certainly to the great-great-grandparent scale on that, and I don't know how many there are.
Anyone else have a question or comment for Dr. White? As a reminder, Will has kindly agreed to hang out in the hall for a few minutes afterwards. If you'd like to shake hands with one of the great scientists of all time, and certainly one of the most beloved, feel free to greet Will in that way. Thank you for coming. We look forward to seeing you at the next NSS Luminary lecture.